I started this video last week and I actually made it too big and then it wouldn't upload, so I've got to start again. So 10.1 was looking at linear motion, vectors and scalars. This is an idea that we covered last year when you were in grade 10. The idea that some quantities, and a quantity is just, something that we measure, some quantities have a component more than just size. They have direction as well. So we say they have magnitude and direction, and these are vector quantities. So things like acceleration and force have a direction that they occur in. So they're vector quantities. Quantities which just have magnitude are scalar quantities. So that's the way we're used to thinking of them. Some of the scalars and vectors have counterparts. So there's length is the scalar, displacement is the vector. So it would be a distance, say in meters or kilometers, but with a direction. Some textbooks use the word position instead of displacement. And that displacement is always measured from the starting point. When you're adding your vectors together in a minute, you'll be ending up with a reference to where you started from. So we've done a little bit of that. Speed and velocity are the matching terms as well. So speed would be meters per second or kilometers an hour, but a velocity will be so many meters per second east or so many kilometers per hour towards north, something like that. So then they've gone through here some different ways that you can represent directions. In year 11, you only have to work in a straight line. So it'll be east, west, north, south, left, right, up, down. You don't have to worry too much about all these other directions just for the moment. So they've got an example here. Here's your starting point, and they've given the direction up, the positive direction. So this is positive. So if the question or whatever you're working on says that the ball went plus 15 meters, that means it's gone directly up 15 meters. If it had gone negative 10 meters, then it's 10 meters down below its starting point there. Rightio, and to represent a vector, they use an arrow. Now, when you first start off doing it, you usually start off drawing these arrows to scale. So this one is 30, this one here is 60, so it'll be twice the length, and the arrowhead represents the direction of the motion. Right, so you can go 30 meters east, 60 meters west. If you've declared that east is going to be your positive direction, then that would be plus 30, and this would be negative 60. It doesn't matter what direction you choose as your positive direction, as long as you work the other ones in relation to it. So if east is positive, west is negative. Right, and this is the sort of thing you might have to look at more next year when you've got these vectors going off at different angles. Now we're supposed to put this little arrow on top of the velocity here to show that it's a vector. I'm very lazy and I tend not to do it. And I notice in the answers and the working, a lot of people don't seem to do that in their actual working. Some textbooks will use a bold font to show that it's a vector. We're not going to worry about it too much. All right, distance and displacement we talked about already. Displacement is going to have a direction. It could be shown as east or west, or it could be shown as positive or negative if you've declared somewhere that east is going to be the positive. The interesting thing here now is they get on to adding vectors. So this might be a situation where someone is rowing a boat, say, or driving a boat downstream, and they're going with the current. So the river is actually adding to their velocity, and you add vectors top to tail. So the top of this vector goes to the tail of the next vector. And it actually doesn't matter what order you add them in, you end up with the same result. And the single vector that is equal to the two of them added together is called the resultant. And when you draw that yourself in your books, you give it 2 arrowheads. So that's the traditional way of signifying that it's the resultant. Right, next case, we've got a person going against the current, the river's pushing back. So the overall resultant is that their velocity is decreased. They've got a smaller velocity. But again, it's top to tail to work that out. Right, and then they've got talking about how we worked out change in temperature. Temperature is not a vector, so that's how you would do a scalar. They've got an example over here. There's a mistake there. It should be a 6, not an 8. So they've got a ball strikes a wall at -10 meters per second, so to the left. So they're saying right is positive, which is usual, and rebounds at a velocity of 6 meters per second. So mathematically, to the right was positive, so it's plus. I'm going to take final take initial. So 6 minus the -10 that you started off with. It was going -10 and it was going -10 and then it hit the wall and went back at 6. So overall, the change in velocity is 16.